Everyone. Today we're going to be doing stacks, everything you need to know in order to get a job. So let's just get into it. This is probably one of the faster videos for data structures. So the stack data structure is pretty much precisely what it sounds like, a stack of data. Probably I'll just also just make a copy of this up here so you get to see what this data structure looks like. But it's pretty much a stack of data. You can see two is at the bottom of the stack, one is at the in the middle, and fourth is at the top of the stack. You could think of it like a stack of pancakes, a stack of um, plates. But I think, yeah, the closest or the best analogy that I like to use is it's like a stack of dinner plates. Like once you add a plate to the stack of plates, like you pretty much like add plates to the top. You can or you can like take it off the top. But once you add a plate to the top of a stack like this, the easiest one to take off is the last element you put on. So I put five there, and then I when I pop, it comes out. So that's pretty much exactly why it's considered LIFO or last in first out ordering. It's because pretty much like the last element that you put in is the first element that's gonna come out. So in certain problems, it can be favorable to store data in a stack rather than in an array, or rather in a queue, or rather in a like other data structure. Like I mentioned in one of my other videos, depending on this data structure you use, it could significantly improve the performance of your algorithm. So some algorithms you have to like you use the most optimal way to achieve best results in that algorithm is to use a stack. Pretty much stacks can be implemented in two ways. It could be implemented using an array or implemented using a linked list. Um, as an array or linked list. So pretty much when you implement it as an array, the only downside is it's that like some of the push operations become O1 amortized, but that doesn't really matter because you get a lot of simplicity by using a dynamic array, and you still get O1 amortized, which is essentially O1. Um, so a lot of people just implement it as using an array, but I think I'll show how to use an array and a linked list and implementing stacks from scratch. That's a separate video. But stacks pretty much have these operations right here. Let me just squeeze this in there. DFS. Oh yeah, it can be implemented as an array or linked list. So for example, if you're gonna do a depth first search or parenthesis matching, using a stack is a really good way to solve those specific problems. And the operations that we care about for stack is pretty much pop, push, peek, and then checking if it's empty. So let me get this back in here. So pretty much popping is what it says right here. It removes the top item from the stack. So pretend I have 412. If I do a pop here, the element that I'm going to get is 4. Yeah, we'll get 4. That's a return. If I have a stack like this and I push element 5, it goes on the top of the stack. And then if I pop again, I get 5. So like the most common thing to remember is like last in first out. And then what's peek? So that's pop and push. Peek just returns the top of the stack, but doesn't actually pop that element out. So if I do a peek, we pretty much if I do peek, we should just return 4. So it returns the top of the stack without popping it out. And is empty returns true or false if and only if the stack is empty. So if the stack is like this with no elements, we return true because that means it's empty. If it's like this, we return false. Pretty simple operations. But like similar to like unlike an array, if you implement a stack using a linked list, you don't get constant time access to the ith element. But a lot of times when you're using a stack to solve a problem, you don't care about that. You just care about what's the top element. So you literally only care about these two operations to solve the problem, like popping and pushing and peeking the top element. So if you use a linked list, it doesn't offer constant time access, but you can use an array, so you can actually get that. Um, and pretty much, if yeah, depending on if you use a array or linked list, you can get constant time adds and removes from the end. But yeah, I hammered it in a lot of my videos, but like using an array is O1 amortized. So cool. Let's just like walk through like an example. I think showing examples of how a stack works is like the best way to do it. So like I said here, the closest analogy is like a stack of dinner plates, and it's in a last in, first out sorting order. So let me just copy this down here. Why did I do that? So pretend we have a stack. Let's just put an empty stack, right? So we're saying last in first out. Pretend I'm just putting a stack full of full of letters. Like we have different letters A, B, C, all the way to like Z. When I push an element to the stack, um, let's grab the specific operations we even care about, and let's kind of order them. I care about pushing first, because why would you pop an empty stack? So push element. So pretend we do these operations. I'll just write some code here. We have a stack. We instantiate a stack, right? Then we want to do certain things. We want to push. We want to take the stack, and then we want to push. Sorry if you hear there's something happening outside, but if you do stack.push, you get A. You do stack. You want to push B, and then you want to do stack.pop. And I'll say you want to do stack.pop, and then let's also do stack.peek, and then let's do stack.pop again, and then you do stack.isEmpty. So we initialize the stack. We first want to push A. So what happens is we pretty much push A on top of the stack. Then we want to push B. So that pushes element B here, right? Now, when we pop, since it's last in, first out, B was the last element to come in, so it's the first to come out. When you do pop, you actually get B here, right? It pops this guy out. So let's just go in and pop B out. You get that, right? And now, when we peek the element, we're gonna get we're gonna get A here. But like I mentioned, peek returns the top of the stack, but doesn't actually pop it out. So if we do like pop finally, we should get A here, and it should take it out of the stack here. So let's do that. Yeah, you pretty much get that. And then that returns A. And now if you do isEmpty, you get true. Super quick example of why we care about stacks. I think just know that it's the closest analogy is pretty much dinner plates. It's when you're stacking dinner plates, you don't really care about the ones in the middle. When you want to grab from the dinner plates, you usually grab from the top because that's the easiest. So when you push something, it puts it on the top. When you pop it, you grab from the top. You can look at the very top element. So it's a last in, first out data structure. And in certain types of problems, it can be favorable to store data in a stack rather than an array for things like parenthesis matching and depth first search. Arrays can be linked stacks could be implemented either as an array or linked list. You'll see that's also a common trend with queues. You can implement queues as an array or a linked list. Um, and pretty much arrays are the most simple way to do it, but you can implement it using a linked list if you want like the most optimal approach possible. So yeah, that's everything you need to know about a linked list. Hope that example helped, and I'll see y'all in the next video.